Welcome back to Applied Mathematics. In this video, I want to review some of the concepts related to exponents and roots. So let me get my head out of the way and I'm going to dive right in. Remind you that an exponent, x to the n power, means x multiplied by itself n times. And a root is the inverse of an exponent. So the nth root of x to the n is equal to x. Although I immediately have to put a giant asterisk next to this because that equality doesn't actually always hold true. Right? Sure. 3 squared is 9, and the square root of 9 is 3. But negative 3 squared is also 9. So why isn't the square root of 9 negative 3? Well, we needed to establish a convention. We wanted the square root to be a well-defined operation, so it has to have only one possible outcome. The square root of 9 cannot be both positive 3 and negative 3, and mathematicians chose positive 3 as the usually more helpful variant of the two options. I'm getting a little bit ahead of myself, but this is why when you are solving an equation that has a square in it and you take a square root, you often have to introduce a plus or minus into the equation. The reason for that is that the square root only gives you the positive branch and you lose the information of the negative branch. Of course, for other roots, this is not a problem. How about the 2 cubed is 8, and the cube root of 8 is 2. Negative 2 cubed, well, negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is negative 8. And the cube root of negative 8 is negative 2. So when your exponent is odd, you have no issues with roots. When your exponent is even, you can have issues when you're dealing with negative numbers. That's something that's going to come back to us much later on in the course when we look more carefully at solving equations involving exponents and when we look more carefully at roots. For now, just that surface level understanding is good enough. I should also mention at this point, if you try to take the square root of a negative number, you get what's called an imaginary value. Again, we'll talk about what that means a little bit later on in the course. For now, just knowing that is good enough for you to get through. All right. So, one of the nice things about exponents compared to the other operations that we've talked about is that even when you're dealing with an approximate value, the exponent itself should always be an exact value. It's always going to be an integer value. There is a related concept called an exponential, which is different from an exponent, where you can have any number in the exponent of the expression. Once again, we'll get to those a little bit later. They're a little bit beyond what I want to talk about right now. All right, so we have an approximate value raised to an exact power. And whenever we have that, we can round using the rules of accuracy. If I can hit the right button and get my calculator to show up, I can take 2.37, I can raise it to the third power, my calculator gives me this ugly number, 13.312053. But since my initial value only had 3 significant digits, I am only going to write down 3 significant digits of this result. We'll call it 13.3. The same thing happens with roots. If I want to take the root of 12.68, well, I can punch in second squaring gives me the square root. You can almost see it in blue above that there. And then we have 12.68. And when I punch that into my calculator, I get this number, 3.5608, etc. But because I have 4 significant digits in the value I start with, I approximate and just put in the first 4 significant digits. That's going to be 3.561. All right. There's other things that we can talk about for now with exponents and algebraic expressions. My expectation is that you've not really done much of anything with roots and algebraic expressions beyond maybe saying something like the square root of 144 square feet is 12 feet, right? The square root of square feet is feet. We'll talk more about algebra around roots later on in the course. For the rest of this video, I'm just going to stick with exponents. And there are a couple of rules, 3 of them that I really want to make sure that you remember. The product rule. If you are multiplying like bases, you add the exponents. So x cubed times x to the 5th is x to the 8th. If you are dividing like bases, then you subtract the exponents. So x cubed divided by x to the 5th is x to the 3 minus 5, which would be x to the negative 2. And then related to that, remember that a negative in an exponent says push it to the denominator. X to the negative 2 is 1 over x squared. Depending on your particular field of study, there are 2 conventions. One of the conventions says you should always have exponents, or you should always have negative exponents and you should never write fractions. The other one says you should always write fractions and never write negative exponents. In this course, I'm going to stick with the always fraction rule because, quite honestly, I think it's easier. But just remember that they are the same, and depending on where you are going with your career, one or the other might be useful. Although seeing a variable like this is probably not going to be common, these rules are far and away more commonly needed dealing with units than dealing with variables. Anyway, continuing onward. The last rule I have is the distributive rule. If you have 2 things, let's say 3x raised to a power, let's say squared, well then you square each of those things in turn. 3 squared, x squared. Of course, 3 squared is 9, so 3x, the quantity squared, is 9x squared. And you can combine all of these rules into one expression if you need to. So if I have 2x squared over x cubed, the whole thing raised to the 4th power. I can't imagine why I might have that, but if I did, I could take x squared over x cubed, rewrite it as x to the 2 minus 3. 2 minus 3 is, of course, negative 1. I could then distribute, so I have 2 to the 4th and x to the negative 1 to the 4th. Well, x to the negative 1 to the fourth would just be a whole bunch of using the product rule. So it would be negative 1 plus negative 1 plus negative 1 plus negative 1. I guess that all told is negative 1 times 4. All right, from here, finally, I'll get around to saying that 2 to the fourth happens to be 16, and x to the negative fourth is 1 over x to the fourth. All right, so we can put all of that in one expression if we so desire. I really hope that we can avoid that for the most part. But then finally, I want to remind you that when you have addition inside of your parentheses, all of the rules go out the window. There is no simple shortcut rule for x plus 3 squared. You have to write it out as x plus 3 times x plus 3 and go through all the multiplication. In this case, you would get x squared plus 6x plus 9. It's even worse if you have a higher power. If you have x minus 2 to the fourth power, well, that's going to be x minus 2 times x minus 2 times x minus 2 times x minus 2, 4 of them. And maybe we want to group and multiply those guys together and multiply those guys together. X minus 2 is x squared minus 4x plus 4. And conveniently, it's x minus 2 times x minus 2 again, which is, again, x squared minus 4x plus 4. Then we have to multiply these things together. All right. Well, luckily we are familiar with those rules. We just reviewed them. It'll be x to the fourth minus 4x cubed minus 4x squared. I'm sorry, that'll be plus 4x squared. And then we'll have minus 4x cubed minus 16x, plus 16x squared minus 16x. These terms are too similar and I'm having trouble talking about them and keeping them all straight at the same time. This is why it's important to take your time and be careful as you go through these. But adding all of that up, it looks like I have x to the fourth minus 8x cubed plus 24x squared minus 32x plus 16, if I got everything correctly. All right. Not a whole lot there because most of it just boils down to remember things that you've done in the past. But hopefully all things that you've remembered, all things that are coming back to you now that I've gone through that review. I'll wrap up with that. As always, thank you for joining me. I'll see you next time.